Okay, Bismillahirrahmanirrahim. These are a set of solved examples from chapter 17 or dynamics. In addition to a few examples we solved in the class, we have these few more problems from the back of the chapter. The first is a basic problem that asks to determine the moment of inertia of this thin ring about the z-axis. This is out of the page. About the z-axis, and the ring has a mass of m. So according to equation at the end of the book, the chapter, this is the integral from 0 to 2 pi of rho a, this is r d theta, integration with respect to theta, r squared, so it reduces to 2 pi rho a r cubed. And we have the mass. You integrate this over the entirety of this from 0 to 2 pi. So you have, this is r, and this is like a section, and this is d theta, and this guy is r d theta. So I'm going to integrate this all through. So m is the integral from 0 to 2 pi of rho a r d theta, which is 2 pi rho a r. You can see in this one of these r's with these variables, this will give you m. So this moment of inertia is equal to just mr squared. Another basic problem is determining the mass moment of inertia of this pendulum, which has a rod, slender rod, and a sphere, which has a mass of 15 kilograms. This has 10 and this has 15 kilograms. So we want the moment of inertia around this point O. You see right away لأن هذا مفصل لك هذا لماس وهذا لماس, so you can subdivide this into two segments. أول شيء the rod وبعدين the sphere. So the moment of inertia of this slender rod is given by 1 over 12 ml squared. This is L, 0.45, and the mass of the moment of inertia of this rod is given by 2/5 mr squared. So we use the parallel axis theorem. So this is, as we see in the book, O, the summation of moment of inertia of G plus md squared. And these are just what I said, 12, 10, 0.45 squared plus 10, this is 0.225 squared. And then we'll close this and start, this is the sphere one, so 2/5 of 15, the mass times 0.1 squared plus 15, again 0.55 squared. This will be 5.27 kilogram meter squared. Let's continue with examples. We did these on equations of motions, and we solved these in class. Let's do a couple of problems. This one involves guessing and repeated calculations. Let's talk about this later. Let's do this problem instead. So you have a crate of mass m, which is supported on a cart of negligible mass. So the mass only due to the crate. I want to determine the maximum force that can be applied a distance d from the cart bottom, so this is d, without causing the crate to tip on the cart. So if you push hard enough, this will fall this way. So if you draw the free body diagram, you have a crate and you have a force P and you have طبعا mg, this is x, so this is y, and you have a normal force concentrated here, so this is N, and you have a force for friction force through this point, and you can require NC to act as a corner if you want to investigate the tipping over process at corner B. So if you sum the moments, it will be P times D in this positive direction minus mg, the weight, times B over 2, and this is equal to ma for the center of mass times h over 2. And when you solve for P, this is equal to summation of forces in the x direction. This P is equal to mag. So PD minus mgb over 2 is equal to P, if you substitute this in this, so this is ph over 2, and you have the maximum P allowed is equal to mgb divided by 2d minus h over 2. And that's the maximum you can do without tipping over. So this example has a mountain bike with a mass of 40 with the center of mass at point G1, so here, and the rider has a mass of 60 with mass test center is at G2. And when the brake is applied to the front wheel, it causes a bike to decelerate, so at a constant rate of 3 meters per second squared, so it's a deceleration, so minus in this sense. Minus acceleration. I want to determine the normal reaction the road exerts on the front and rear wheels. You assume that the rear wheel is free to roll, and another assumption will just say this leaves the road very slightly, so that we eliminate the moment about this normal force. This acceleration can be obtained directly by applying this equation of motion, moment equation of motion about this point A. So the summation of moments about point A positive. This summation of moment is M for the K. ما عندنا الاثنين اللي هو البايك والأخ الرايدر about point A. So this will be minus 49.81 times 0.4 minus لأن هذا it's a negative sense, so this is positive معناته this is negative 0.4. وأيضا عندنا this guy is also 60 times 9.81 mg, وهذا راح يصير 0.4 و 0.2, so this is 0.6. And all of these are equal to the moments MA, basically الماس مال هذا والماس مال هذا times the acceleration, نفس acceleration. So this is minus 40A اللي ما ندري شنو, they have the same acceleration, times 0.4 اللي هو هذا 0.4 minus 60 مال الرايدر 981 times 1.25. This will give you an A is equal to 5.606 meters per second squared. Next, we'll do the crate problem. We have a crate with a mass of 50 kilograms and rests on a cart having an inclined surface of 15 degrees. We want to determine the smallest acceleration in the direction of the force that will cause the crate to either tip or slip. And we want to see what the magnitude of this acceleration is, and the coefficient of static friction we are given mu s as 0.5. Let's assume first that the crate slips. For the friction force, 0.5 times the normal. And we don't know what the normal is, but we're given that mu s is 0.5. You can draw the free body diagram. You have this crate, and you have mass of the crate, mg, and you have friction force, let's say this slips, and you have a normal force that I don't know what the exact location of. Let's assume this is the middle of the crate, this is 0.6, and this is 0.3 and 0.3. So there is a distance, let's call it x. This point is point A. Of course, we have this 0.5, the distance, because this is 1 meter. So if you sum the moments, it's counterclockwise in positive direction, moments about point A, this will be equal to all the moments of all the forces about point A. You can resolve this, the weight, into the x and y direction. This is the x prime direction, and this is the y prime direction. You can't do xy الحين we'll transform it into x prime and y prime along the crate surface. So this component, this one is mg cosine 15 degrees times x, call this x, 9.81, well mass is 50, and this is the negative one, so it's a counterclockwise, this guy. So this is minus 59.81 times sine 15 degrees. The moment of the arm is 0.5 اللي هي نص 1 meter. And all of this is equal to the MA as given by kinetic diagram tells us that you have an acceleration. This is m times a, which we don't know what a is, and this can be resolved into x prime and y prime direction. So this is component is another component. We could write this as 50a cosine 15 degrees times cosine here, this is 0.5 plus 50 times the acceleration sine 15 degrees times x. So resolved into 0.5 for the x direction, this is the cosine thing, and this one is x for the y direction, the moment arm in the y direction. I don't know what x is, but this is the sine term. So all of this is equal to these two components. This is equation 1. I have one unknown and another unknown. I have one equation, two unknowns. But I have two other equations, summation of forces in the y prime and x prime directions. So this I can summation of forces. This is positive in the x direction or y prime direction. Say this is y prime. All of these are equal to ma for the center of gravity in the y prime direction. So this will give you n positive minus mg 59.81 cosine. That is equal to minus 50a, the unknown, sine 15 degrees. This is pointing in the negative y prime direction, and this is the y prime direction. Like this one is positive in the negative x prime direction, negative y prime direction. Okay, so I have another equation which is summation of forces in the x prime direction, summation of forces, where this is the positive direction. This is equal to ma on the center of mass in the x prime direction, equal to m 50 times 9.81 sine المرة 15 degrees minus 0.5 n, لأن this guy is in the negative x prime direction, in normal. So normal is this way, and it's resolved into this component and this component. So this will be a negative sign. And these are equal to minus 50a, acceleration unknown, cosine 15 degrees. So عندي acceleration هذه أبي acceleration in the x direction, component of this, which is the cosine 15. عندي unknowns زيادة هني، ال a هني وال a هني، ولكن عندي أيضا ال n is unknown وال n is unknown. So three equations, three unknowns. معناته I'll solve them together and I'll get n is equal to 447.1 Newton, and the acceleration is equal to 2.01 meter per second squared. The x is also 0.250 meters. From this value, what is the magnitude of acceleration? We got this, and the coefficient of friction. I made an assumption بالبداية and I assumed the crate will slip, and the coefficient of friction is 0.5. So I made all the calculations under this assumption. ألاحظ أن السنتر from rotation x is على بعد 225 سنتي. So it's less than 0.3. هذا هنا 0.3 و 0.3. So it will try to rotate around this point, so it will not tip, it will slip. If it were the other way around, rotating about this, معناته it will fall down. Let's do this problem, which is about rotation about a fixed axis. We have a shaft BC that is rotating about this axis Z with a time-dependent moment, where t is in seconds, and you want to determine the angular velocity, so alpha, of this rod, which weighs 3 kilograms, when time is 4 seconds, starting from rest. So moments from 0 to whatever this final value is, and you want to neglect the mass of this shaft, BC. So we could start by writing the mass moment of inertia of this rod about the z-axis, which is I(z), which is I sub g plus md squared. This is 1/12, 3 kilograms, times length, which is 0.3 squared, plus the mass times d squared, 3 times 0.15 nus squared. So you calculate this to be 0.09 kilogram meter squared. Since this is rotational, F is equal to ma will be the summation of moments about the z-axis is equal to I alpha, del ma. Let's substitute all of these. You'll have the moments. This is given by this expression, 0.45 t to the 1/2 equal to 0.09 alpha. So let's solve this for alpha in terms of t. So this angular acceleration is equal to 5 t to the 1/2 in radians per second squared. I return to the kinematics, and you'll find that the integral of d omega is equal to the integral of alpha dt. So I'll integrate this from 0 to omega اللي I want, angular velocity that I want, and this from 0 to التايم اللي عندي اللي هو 4. So this will be integral from 0 to omega d omega equal to 0 to t of this guy اللي هي 5t to the 1/2 dt, which will give omega as a function of t as 3.333 t to the 3/2 radians per second. So evaluated at 4 seconds, this will be 26.7 radians per second. Let's look at a couple more problems. Let's look at this problem where you have 15 kilogram block A, 20 kilogram block B connected by light cord, so the mass of the cord is insignificant, over a 5 kilogram pulley. So this has a moment of inertia, it weighs 5 kilogram disc. If the system is released from rest, determine the cylinder's velocity after it has traveled downward 2 meters. So we have to get the equation, get the acceleration and expression for the acceleration of this block, and then use the kinematics of chapter 16. The coefficient of friction, 0.3 between block A and the surface, and this cord doesn't slip. So the free body diagram could be drawn as this block with a friction, with a normal here, and a weight, like a 9.81 Newton. You have a cord tension here, and you have block that is 5 kilograms, times 9.81 Newton, and you have this moment is 0.1 meters, 100 millimeters, and you also have the weight of the second block, which is 29.81 Newton. So we'll say that this is X and this is Y. This is equal to kinetic diagram that has this block going with an acceleration of 15a. This goes around the pulley, which has an acceleration of 0.025 10a, because this alpha is a over r, and this is a over 0.1, so this is like 10a, and you have, this is 0.1 in a, 0.1 millimeter, and this one is then 0.1 meters, or 0.1 meters. You have a mass of block B, which is 20 times A. So you write the moment equation of equilibrium about point O هذه, and you'll get the summation of this plus in this direction moment about point A is equal to the summation mk about point O. أول شيء you notice in the moment of this guy and this guy they cancel out لأن they're the same distance هني وهني. So this reduces to the 20. So this is 20 minus 20 actually, then the other way, the other counterclockwise. So this is 9.81 times distance اللي هي هذه to the chord. So this is 0.1 is equal to summation of كل هالmoments. So this is 1 minus 15 a 0.1 هننسى ال 0.1 فيهم كلهم. This direction and this one also this direction and this one is in this direction, so all of them, so minus 20 a 0.1 وماينس ال 0.025 مالت الويل 10 a نفس ما we calculated هني. So this is, you have one unknown, 1 the only unknown, so this a will be 5.232 meters per second square. Now, since the acceleration is known, you use the kinematics and you'll say that v square is equal to v0 square, that started from rest, plus 2ac, which is constant, s minus s0. V square is equal to 0 plus 5.232, we just calculated, and we have 2 meters. So minus 0. This will give you v is equal to 4.57 meters per second after 2 meters. Let's look at one more equation, one more problems, or one more example other than the ones we did in class. Let's look at this one. So this 20 kilogram punching bag has a radius of gyration about its center of mass of 0.4 meters, and it's initially at rest and is subjected to horizontal force of 30 Newton, and we want to get the initial angular acceleration of the bag and the tension T in the cord AB. So there's a cord that holds it together upward. Let's do, this is a general plane motion. So we'll start with the summation of forces in the x direction. مثلا fx, summation of fx is equal to ma of the center of mass in the x direction. So we have the 30 here. So 30 to the positive direction, and that's the only thing. The mass is 20 of the punching bag, and AG in the x direction. So that's one equation, one unknown. Another equation is when you have the summation of the forces in the y direction. So this is MAG in the y direction. You have the tension in the positive direction, and you have minus the weight mg. So 20 times 9, 20 times 9.81 are equal to 20 times the acceleration of the center of gravity in the y direction. Of course, the free body diagram tells us this is just T, and this is F, اللي هي 30 Newton, and this is the mg, اللي هي weight, 20 times 9.81. The kinetic diagram will have a normal component of the acceleration, so A in the normal direction, and you have an acceleration A of the bag in the tangential direction. So this is 0, and it's not moving anywhere toward the center or away from the center, but this one is, of course, you have what we have here, acceleration of the center of mass in the y direction and the acceleration of the center of mass in the x direction. And we know initially it was 0, but we have an alpha that we have to calculate, initial alpha. If you sum the moments, let's say in counterclockwise is positive, so m moments about g, these are equal to the mass moment of inertia, alpha. So you have 30 times 0.6, is equal to 20 times the moment, this is 0.4, the distance between this and the center of rotation, squared times alpha. So we have more unknowns here, but we know from equation 1, let's say this is equation 1, that A of g in the x direction is equal to 30 over 20, so this is 1.5 meters per second. And for this general plane motion, we could write the acceleration of the bag, point B, is equal to acceleration of the center of mass plus AB relative to G by definition. And these are all vectors, of course. So the acceleration of the bag, this point A, in the I direction will be equal to the acceleration of the center of gravity in the J direction plus the acceleration of the center of gravity of the bag in the X direction, and this is I, minus alpha 0.3 I. It's easy to see in the J, this is only J, so this gives AG in the Y direction is equal to 0. ماكو شيء يسحبه بعيد أو قريب. You equate these three and equation 2, you'll see in the tension will be 196 Newton. Let's do one last problem. This is a lone roller which has a mass of 80 kilograms and a radius of gyration of 0.175 meters, and it's pushed forward with a force of 200 Newton. When the handle is at 45 degrees, we want to determine the angular acceleration of this wheel or roller, and the coefficient of static and kinetic friction between the ground and the roller are 0.12 and 0.1 respectively. So the forces are 80 kilograms times G, so 80 times 9.81 Newton, and you have a force of 200 Newton in this direction with an angle of 45 degrees and a normal through A and a friction force through A as well. Normal through A. So summation of forces, we'll do this is X and this is Y, and we'll say that this is the acceleration. We'll say that this is the angular acceleration, alpha, of the center of G. So this is AG. And we'll do the summation. Let's say this is, to the left is a positive, so summation of forces Fx is equal to MAG in the X direction. I'll have the components, this is 200 cosine 45 degrees minus FA, which is the friction here, and this is equal to ATA of the center of mass. Also I have, this is one equation, I have another equation, summation of forces in the Y direction, AG in the Y direction, and this will give me normal at A minus AT 9.81 minus the component of this force, so this is sine 45 degrees, and all of these are equal to 0. Lastly, we can sum the moments about the center of gravity, so this is the summation of moments about G, and these are equal to the moment of inertia times alpha. So this I have force A, friction force, with this radius of 0.2 meters in this direction, positive direction, are equal to 80 and 1.75. I'm given 0.175 with the radius of gyration squared times alpha. So if you assume no slipping, this catches the ground, the circumferential acceleration is related to the actual acceleration AG. So we have, so let's say assuming no slipping, the acceleration of the center of mass is just 0.2 alpha. If you do this and you carry on the calculation, so this is the assumption that closes the number of knowns and unknowns. So you'll have F at A, friction force 61.32 Newton, and the normal at A 926.2 Newton, and lastly alpha 5.01 radians per second square. Now we have to do one last check. Since we have this normal force, we can check in FA maximum allowable is static friction times this normal at A. So this is 0.12 اللي I'm given here times 962 or 926 fun, and this will give you 111.1 Newton, and this is the maximum allowable. And what I have here at 61 is fine. So this is greater than 61.32 Newton, so it will not slip. It will be static friction.